Und brauchen wir das höher?
Ja, das würde ich machen.
Mhm.
Yeah, so we expect K to minus 5/3, and we see the gray color on the sky with evidence that it is really K to minus 5/3. Put the camera there. Put it there. Not here. Not here.
So this is power 5/3.
So here's the result by Biscam and Miller, and we see with normal viscosity, with now an MHD simulation though, with normal diffusivity, we see that we have a compensated spectrum which is flat, which suggests that very strongly we do have a strong evidence that there is neither bottleneck effect nor any deviation from K to the minus 5/3. And then on the other hand, if you use K to the minus fourth order hyperviscosity, you see that the entire inertial range is modified. The entire inertial range, not even just near the bottleneck, actually everything is modified.
Yeah, of course.
But of course.
Yeah, because you change diffusivity.
Yeah, but why should the entire inertial range be modified? Do you trust? Do you think that's right? Or is that an artifact of the setup? It's a decay simulation, by the way, I should emphasize.
Decay turbulence.
Yes.
Okay.
And that means things are not completely straightforward.
So in these simulations, there is Laplacian, and there is additional term with Laplacian square.
Yes.
And sign here minus.
Yeah, but then there's no Laplacian whatsoever.
Yeah,
it's just
no,
into the fourth. Yeah. Okay, so we really don't know, and what one has to do is do a simulation where the numerical effects can be excluded as an argument, where we can address whether or not we have physical effects, where the Reynolds number is hopefully big enough, and where compressibility effects may also be excluded as a possible reason. So this is what I represented here. And we really needed, I mean, even though these simulations were available already back in '98, we didn't really know the answer, and one had to wait until the 4,000 cube simulation became available to really address this issue. And this was then done by Kaneda and company, who calculated on the Earth simulator at 4,096 cubed the power spectrum, and what they find is the black line. And they find a compensated power spectrum, compensated with e to the 5/3 power. They find something which is essentially flat, but there is a strong correction of 0.1, which is more than we expect from Chelevec scaling, which would be 0.03 minus, the sign is right. But then we also see a strong bottleneck effect. So now we can address some of these questions here. We can actually say that the bottleneck effect seems to be real, because at least they find it.
Real in computations or real in laboratory?
Real in computations, first of all. So it's real in computations. Compressibility was not the reason, because it's an incompressible simulation. Reynolds number too small. Yes, in some sense, yes, because now. No, it's not, because in most cases they were, at 1,024 cubed they were already big enough. If you actually do a 512 cubed, you don't see the bottleneck. We know this now. We don't see this very well because the Reynolds number is actually too small. So in order to see the physical departure, the Reynolds number has to be large. So the fact that you see the bottleneck because it's too small was not the right answer. And there was also not numerical then, because this is using spectral methods. Now, two things here. The first is we have done a hyperviscosity simulation with Haugen in 2004, and we find a strong bottleneck, even stronger bottleneck effect. this is clearly numerical then. So if you use hyperviscosity with delta to the 6th power here in this case, you clearly get a numerical effect. However, it's not correct that, as it was suggested based on the simulations by Biskamp and Müller, that the entire inertial range is being modified, because you see here that the entire inertial range is actually having the same correction of k to the minus 1. Minus k to the minus 1. Same correction. So the inertial range is already correctly reproduced, even with hyperviscosity. And thirdly, we do Smagorinsky viscosity, which is the poorest, but perhaps still one of the best subgrid scale models. Not maybe exactly the best, but it's certainly one which is, as opposed to hyperviscosity, which is known not to converge to Navier-Stokes. Smagorinsky is known to converge to Navier-Stokes equations. So we do get now not only the same 0.1 correction, but we also get the same height of the bottleneck effect. So Smagorinsky reproduces the same bottleneck effect. So these were all motivations. Here's something else about the bottleneck effect, because you were asking whether it's real or physical. One clue that has not been mentioned is that there's a difference between 3D and 1D. And of course, whenever anybody does anything in the observatory, in the laboratory, they have a one-dimensional spectrum.
In laboratory?
Anybody who has a three-dimensional spectrum in the laboratory?
Also built 3D.
It's a good question. We build both. Sometimes 2D. Normally,
But not with many detectors, right?
We use
so we both.
So then you should be able to verify that there is a difference between the two, as is also verified from the simulations here. You see a bottleneck in 3D and you don't see one in 1D. And of course the result is well understood. However, this was back in the 50s, and even many of the experts didn't remember anything anymore, because the one thing you do remember is if you take a power spectrum in a one-dimensional spectrum, it becomes the same power spectrum in 3D. But here we are talking about a situation where we have a change in the slope. So we have something like this. We have a power spectrum and we have this. So in this range, can you say you have a power spectrum? Of course not. You have a serious deviation from power spectrum. So therefore, in this range, you cannot expect this analogy between 3D and 1D to be the same anymore. And the result you see quite easily here. In 3D, what we do is we do the power spectrum by calculating full transform in 3 dimensions and averaging over or integrating over spherical shells, as it's done here. If you compare this with the one-dimensional power spectrum, what we do is we just do a full transform in the z direction in this case, and we use an integration over the x and y directions in order to enhance the statistics by averaging over several pencils. However, this we can then also do in Fourier space by simply using Parseval's theorem and noticing that the integration over x space can also be replaced by integration over wave number space, which is here written in terms of k omega, which is the cylindrical radius in Fourier space. This using an integral transformation of variables, where the three-dimensional wave vector or wave number is given by the cylindrical wave number and the vertical one, can be inserted. That leads to a change of the lower integration variable to kz. And so our final formula, so this is then of course the same as our previous three-dimensional spectrum. And so the one-dimensional spectrum can then be obtained from the three-dimensional one by dividing by k and integrating over k. And that's the same problem as I had a few days ago. And because my power was here, right? This is my power. Yes. These things happen all the time. Battery lifetime is very short. Okay, so therefore, the bottleneck effect we can summarize as now a physical effect.
Physical.
Physical effect.
Physical, but for computations.
Computations means 3D. So if real life is really only one-dimensional and 3D is only possible in simulations, then the answer would be correct. However, if real life is really only, if real life is three-dimensional and it's only in technique that you can only measure it in 1D, then this would be the wrong answer. So the right answer, therefore, is this one. So therefore, when Nathan says he can do this,
But there is only one problem.
you should be able to see that
There
difference.
was a problem. I think
It is never seen in laboratory.
Yeah. And so what's the problem? He says there was a
We
problem.
haven't enough resolution. I think.
Exactly.
But there are other experiments,
Okay.
a number of
And
experiments.
this is
where
just
it was
mathematics,
seen.
right? So all you need to do is just verify that you can reproduce the same mathematics.
Yeah.
And of course, we have done this in. Okay, I mentioned here
This is
another.
pure numerical effect, right? Bottleneck. It's not enough resolution, right?
It says real here.
What in the real?
So real means that it's really there, but you could say, of course, in reality, we have a Reynolds number of 10 to the 11th, and the bottleneck effect would really be, it's a very small scales, and you don't really care at all about this. In that sense, it's true, it's numerical. The reason is really that for the following decades, we are limited to resolutions of less than 10 to the 4th.
Because then we have, kinetic physics and all that.
Oh,
Yeah, this is an additional complication. There's an additional complication.
It never happens.
you will never have a bottleneck.
Well, there are no physical reasons for bottleneck.
No.
Yeah.
I mean, just I have
different physics now. Don't
Yeah.
I have removed a few transparencies, but you do. I mean, it was known there are papers by Shea and Jackson already who had a fit to an observed power spectrum which had a combination of k to the minus 1 and k to the minus 1/3. Just purely phenomenological. Yeah. It's a physical effect. It becomes simply, it's a physical effect which you see in 3D. You see it much, much harder in 1D. But it's there.
Roughly speaking, because normal mechanism of dissipation not enough strong, if we have got enough large energy flux in spectrum, it's idea, right?
That's the reason for it. Yeah, that's the reason why you actually have a physical bottleneck effect. Yes, you're simply disposing of your energy at a point where you have no longer free access to all the triangular interactions, because some of the triangles will be very sharp. They will be very.
You mean triangle from U operator?
Yes, exactly. From the nonlinearity, you have triangular interactions like this, where in the inertial range you have a smaller k, and these k's are interacting with the dissipation range, and there you are all of a sudden stirring in something which is like honey. And if you are all of a sudden disposing of your energy by putting stuff into honey, it becomes harder, as if you were to do it within the rest of the inertial range.
It's not k, it's scales, right?
It's k.
K. One k is small, or practically tends to 0. You mean in...
That's in the dissipation range. Yeah.
So it means it's a local, it's locality. It is a description of locality. Because k is small, but effectively we've got locality of interaction. Right.
So now one little insertion here, which tells you, I mean, you may have gotten the idea that maybe doing something unphysical in the dissipation range, it may of course change everything that really has critically to do with the dissipation range, but maybe not with the inertial range. And so here's one example where which demonstrates that actually everything can go wrong in the inertial range as well. That's badly wrong. And so one of these examples, there's not many such examples that you can find, but in the last 2 years, a completely new method for computations has come on the market, and this is called, that's a code called the Magma Code, which is developed apparently here with Roswell and Price, and they are now abandoning this again after my paper. But the idea is the following. You want to do calculations using SPH, smooth particle dynamics. And you have a serious difficulty in maintaining divergence of B equals 0. One solution out of this is using the three-dimensional vector potential. Another solution is to use the so-called Euler potentials, which we may have heard about. Euler potentials. And the idea then is, let me see. I come to that, of course, in a moment. We just missed the Euler potential physics, which was here. I have it a bit there. So now we talk about the pencil code. And many of you will know about the pencil code, but why it's called pencil code, of course, because you do a calculation along one pencil at any given time, which requires means you can do all the physics by assembling only a small amount of data at any given time. You're not accessing the full three-dimensional data array before you finish actually the entire physics along each point on the pencil. That's why it's called the pencil code. It uses, runs on MPI, has to be used for a number of different applications, and it's scaling pretty good. But somehow my sheet is in. Yes, but many of you may know this, but and I just explained it briefly here. Of course, if you do a calculation of a curve, for example, that means, or any derivatives, that means, of course, you have to access the full three-dimensional pencil, and that's being done by the individual derivative routines. But then the result of such a calculation is only available at any given time along one pencil, which is a structure Irina has seen earlier today, which is such a one-dimensional structure only. Over this length, it excludes the ghost zones, and in this case, it has an additional dimension of 3. These structures don't require much memory at all, and you can easily and quite freely allocate as much memory as you wish, in particular if it's of computational advantage. Like, for example, if you want to define complex matrices, if they were all three-dimensional vector fields, they would pose a serious restriction on the overall memory that you can use.
B, it is 3D vector.
That's a 3D vector. This is X, Y, and Z components, and it's available in the code.
And what is it, NX? It is points.
It's a number of points in the X direction within one processor. So now, since the pencil code meeting in 2007, essentially, which was here in Stockholm, we can already parallelize in the X direction. And since the last pencil code meeting in 2009, we have been persuaded essentially by Anders, who has done serious calculations with X parallelization and has verified that it works for him.
But if I need for 3D...
So I'm using it now most of the time, like just and Alex and I submitted a job 5 minutes ago.
If I need for vector of 3D coordinates, 3 vectors in this sense, NX3, NY3, and Z3, right? If I need full vector.
Full, I mean, a vector in the sense that it has 3 components.
Yes.
But you mean the 3 X positions, yeah? Positions in X space. So in this F array, all the dependencies are included, and they are, by the way, only those points within each processor. So each processor is what you have on one machine. One machine is like a little laptop. It has a maximum RAM of typically 2 gigabytes, and you don't want to use much more. If you want, of course, to do a 4,000 cube simulation, then it will never work on this RAM alone. And therefore, each F array has to be split. I mean, each F array represents only part of the entire domain. Please interrupt me if I'm going too fast here. The other thing that was quite essential when we started doing all of these things is we wanted to have, and this is what Wolfgang Dobler and I initiated in 2001 in connection with a course that we were teaching at a summer school for 1 month in Potsdam in the year 2001. And so because of this, we thought we could not rely on automatic parallelization as we were doing it back then. And that was what Orca has been teaching us. It has been saying compilers get better and better, and we don't need to worry about MPI, we just do everything automatically. And even by the current years, this is not good enough normally. So we started doing, writing a completely new code in 2001, which was essentially meant to work just for MPI, first of all. And then afterwards, we put in all the physics back in again. And this, I think, is another important strategy, which I was recommending at the last pencil code user meeting. There was somebody who wanted to program something on graphics cards. And by running on graphics cards, he was telling us you need to do serious modifications to just about anything. And then I was telling him he should really start with a simple code, which solves, for example, the three-dimensional Euler, the three-dimensional Burger's equation. That's what we did back then. Burger's equation in 3D is just a scalar variable in 3D. Solve this as fast as you can on your graphics card, and don't worry about any physics at this minute. and then afterwards modify the entire thing, put in all the physics, and from the same moment onwards make it a public code. And that way you get everybody else on board. But I come to that maybe a bit later. Much of our physics can be turned on and turned off. So most of the time you don't want to worry about radiation. So one of the things that I brought up earlier in this meeting was that the pencil code has at the moment 200,000 lines. So if you're starting as a new user, you see 200,000 lines, then you would, and that's the rough idea, you are scared, no? But you see already then one big chunk out of this is radiation. So you compile with no radiation, you lose immediately maybe only a tenth, of course. But then you say, I don't do any chemistry, or I don't do any coagulation. You lose again several 100,000 lines. Or you don't have any dust in your stuff. Maybe you don't even have self-gravity. Again, you lose lots of lines. And so essentially, it comes down to just using very simple lines which have to do with I/O. So when we started working with the stuff today, we were using a code which has essentially everything with no. So that means you start really completely from scratch. That's what we did this morning. We started from scratch. We implemented a diffusion term first of all. Then we could run down the diffusion thing. Then we implemented an alpha effect and could run an alpha effect. So completely from scratch everything. The thing that we of course can borrow from the code is that it's the fact that it's doing everything in parallel. Even if you don't do it, you can run it on your laptop. Even on one process, no problem. It's all the same for you. You can... What else? I forget. And the I/O, of course. So imagine if you want to calculate an average density, for example, and you just have this available. How do you do it? You just calculate an average of this. And this doesn't tell you much. This is just the average along one pencil. That doesn't tell you about anything else. You have to sum it up for all the other pencils, and that's not enough either. Because then you have everything on your box. You need to communicate this with all the other boxes, all the other processors. And only then you have the RMS value. So even just a simple thing like, can you tell me the maximum of your velocity, is not completely trivial, because you have to negotiate with all the other processors. Ask them, how much is your maximum, by the way? And so eventually you have everything together. So you can imagine such things are not simple, and you better do it in such a way that it's that each time you want a new maximum or new average or new integral of something, that you don't have to worry much about these things. So that's one of the things you're borrowing immediately from this pencil code, even if there's no physics into it. The other thing that is not really necessary with the pencil code, but that's what we started doing, is we started using a high order code, 6th order. However, having said this, given that everything is modular, of course, that I really did only actually during the pencil code meeting last in Heidelberg. So we had breakfast on one of the days, and then I was telling you that half an hour ago I started implementing a second order thing, and then I was able to tell you over breakfast, right? And the answer was, the question is how much faster is it? People often ask me, why the hell are you spending so much time with your 6th order scheme, which uses schemes like this? You're accessing all these other points. It's extremely expensive. Is it not much faster if you just do nearest neighbors, second order? And then you may use a few more mesh points, of course. So the speed up that you gain by going from 6th order down to a second order, the speed up is 13%. So you gain 13%, but you lose accuracy, and I will show you in a moment how much accuracy we lose.
Oh, but you can gain by failing non-uniform grids, right?
But we can have non-uniform grids with our stuff, and we can have non-uniform grids by retaining 6th order. And we do it by using a coordinate transformation. So our calculation is 6th order. We have a coordinate transformation which is analytic, and therefore we are retaining 6th order, or whatever order we have. So after I've programmed second order, of course I've also programmed 8th order, and then just a few minutes later I've also done 10th order. So you can even run...
shock waves and also shock wave calculation.
I come to that. That is not true. I come to that. In order to understand this about shock waves, one important thing, and that will be your first exercise. So the important thing to realize is that there are numerical or discretization errors. They are not round-off errors, they are discretization errors. They come with the order of the scheme. What it means is if you calculate the derivative of your cosine, you're supposed to get minus sine kx multiplied by k. So if I divide by sine kx, I'm supposed to get the wave number out of this again. But if the numerical derivative is not equal to the analytic one, I will not get the actual wave number, I will only get what is the effective wave number. And that may not be the same. So as you increase the actual wave number, the effective wave number increases linearly up until a certain point. And even if you do a spectral method, it increases linearly to the very last point, except the last point. And the last point, you have an infinite discretization error, because the correct answer is 1 in Nyquist units, but the numerical answer will be 0, even if you do a Fourier transform method. So even the Fourier transform method is pretty good up until this point, except the last point. So if you have something which corresponds to a bigger an up and down thing, that has an infinite, if that's your signal and it's discretized by just these few points, you have an infinite discretization error. The same is not true for the second derivative. The second derivative has a finite discretization error. This is the correct result, which you obtain correctly actually with spectra in this case, which gives you in Nyquist units this one value here, which is 1, otherwise it's pi squared in mesh point units. The second order scheme is worse, the sixth order scheme is better. None of them are really terribly good, but clearly you see the higher order the scheme, the less you see here you can go all the way to 60% of the Nyquist frequency without hardly seeing any mistake, whereas with second order you see the mistake already after 20% close to Nyquist frequency. So now comes the business about how much viscosity you need. And that begins to relate to what you said. People are thinking if you use a high order scheme, you get big Gibbs phenomena. And so if you want to avoid Gibbs phenomena, which means Wiggles, you need to go to a low order scheme. So let's now square this with measurements. So what we do now is we advect a signal like this, and such a signal we have in the such a signal is of course composed of lots of Fourier signals, Fourier components. And here we have done a calculation, just a simple advection equation, which is written down in the next transparency here. This is an advection of a passive scalar. By the way, this is the second exercise. So you're running no hydro, nothing. You just have a constant velocity u. You calculate the evolution equation of a passive scalar, which has an advection term, has a diffusion term. I'll spread like this. And you change the value of the viscosity, which in the previous transparency is called nu. So now we have here a comparison of a 10th order scheme, two different viscosities that are being normalized in units of u and delta x. If you have 0.002 in these units of the viscosity, you have small Wiggles. If you make the diffusion a little bit bigger, the Wiggles become less, and virtually absent. But of course the signal becomes smoother near the jump. This is after having run such a jump signal, such a top hat function for 5 revolutions through the mesh. 5 times through the periodic mesh. You do the same thing now with 6th order, and you clearly see already with the same viscosity that you use for the 10th order scheme, you have bigger Wiggles here. So clearly you see that if you go to a lower order scheme, you increase the Wiggles. You don't decrease. It's not the other way around. It's not like saying higher order scheme gives you more Wiggles. They give you less Wiggles.
Well, it depends on the approximation, of course. Because the Dynamo scheme is of the 0 order.
Yes. So that relates back to the first question. So if you're thinking you can do your high order Reynolds number and your diffusion operator by just having 0 diffusion, if you think that's true, then you should do a Goldenough scheme. And what that basically corresponds to is making sure that you don't have Wiggles. You are having a monotonicity scheme built in. So if you are sure that this is the right physics, then that's fine. Are you sure about this for radiative shocks? Are you sure about this for all types of MHD? What about the intermediate shock in magnetohydrodynamics? We know the intermediate shock in magnetohydrodynamics is a non-uniqueness of the MHD equations. If you have a non-uniqueness, you have a problem.
Well, then you need to change physics again. Then it's because the equations don't describe physics correctly.
I mean, it's the MHD equations and the equations are simply not unique. So yes, whatever the physics is, what our philosophy is that you have to solve the equations as they are posed, without putting in any smart physics. Let me come to another point. It's most likely not critical, but you know that Riemann solvers really only are proven to be correct in one dimension. If you're absolutely sure that there's no problem if you go from one dimension to 3 dimensions, you're fine. Are you sure about this? I should have shown you the transparency about the problem with the Euler potentials a bit earlier, because then you may have been scared. At the moment you're thinking there could not possibly be a problem. And everybody has been showing, I mean, the same with Euler potentials. People have been demonstrating this, that the Euler potentials work correctly, not only just in 1D, they even work in 2D. However, they can also, and this people didn't know, they can be quite seriously correct.
Everything what is said is good, assuming that the first derivative exists, right? That when we approximate it, but if it doesn't, like in shock waves, then what to do?
Let me show you this previous equation here. One of these, jump over this. Yeah. Yes. So these are the equations that were actually stated in the paper by Paul Woodward and company.
You haven't heating in this equation.
Fitting?
Heating.
Heating. Yes. Okay. Now where does the heating come from?
You should put for it. This
heating comes from here.
Yes, but heating I mean is
radiation.
Reaction. Nuclear reaction.
Viscosity.
Just viscosity. No nuclear reaction.
Non-linear source torque.
Chemical phenomena you have.
Non-linear source torque.
Non-linear? It's linear.
Non-linear.
Yes. So the equations as they were posted in the paper by Woodward was this sort of equation. So he essentially put nu equals to 0.
Ooh. Very brave.
Yeah, so what you do is you put nu equals to 0. What?
Yeah.
Of course, you do get heating. They actually wrote in their paper ds by dt. And of course they calculate and they find of course that s is not constant. So they are clearly acknowledging that even though they write it, that's not what they mean. And coming back to the Euler potentials, people are saying it's probably okay. I mean, because it's okay for zero magnetic diffusivity, and it's not okay. They know this actually for finite magnetic diffusivity, but they say we make it very, very small, hardly noticeable, and then you shouldn't see this. And
so you mean numerical viscosity or what?
Yeah. This is normally replaced by numerical viscosity, which for shock waves you know is actually okay. It's not okay already for radiative shocks. That's also well known. Mihalas tells everybody that radiative shocks are depending very much on how thick they are, and they are radiating non-locally. The reason why such an approximation works is because you can take care of all the physics locally within the dump. So it doesn't matter how broad it is. The dump conditions are being obeyed, regardless of.
Yeah, it's also away from.
But if you have a radiative shocks, the stuff is being radiated immediately non-locally away. All the way to infinity.
They don't affect dynamics. It doesn't affect dynamics.
It does.
It's look at the jump.
Yeah, definitely.
I think there are things that are serious mistakes if you do this not correctly. I'm not an expert on this, but the phase speed and stuff like this are most likely wrong if you do a radiative shock with a numerical diffusivity. I think that's
very good. No,
so that was, of course, back then when people were in the war, of course, calculating blast waves for the atomic waves and stuff. And it was all wrong. And afterwards they learned. They talked to Mihalas, of course, and Mihalas told them how to do it.
So, because you don't use diffusion approximation, no radiative transfer is totally different problem It's not local.
Yeah, right. And that means you can. It makes a difference whether the shock is sharp or not. It has to have the precise, correct thickness. And the way to deal with this is, of course, to use a non-adaptive mesh. So that if the shock thickness is really what it is, you have to resolve it, no matter what. There's no way that you can correctly avoid this.
The similar problems are also related with collapse problem, where physics is very important.
Collapse problems. If you mean like the
Milk collapse.
If shocks involved, probably so. Yes, there's radiation, of course. You have neutrino radiation, stuff like this. Yes. So here we see how you can resolve shocks. So the idea is, of course, to resolve the shock with as few mesh points as possible. We see that in order to resolve this shock more or less correctly, you need, in this case, at least 0.5 in units of u and delta x. Deviating by this by just 20% makes the errors compared to the analytic solution seriously bigger. But the higher order, the lower order of the scheme is, the more you still need. Here, the difference are not so big anymore, but here you need 0.8 instead of 0.5. And 0.6 would not be good enough. That's worse than this one is. So even with shocks, it's true you can get away with somewhat less diffusion, even for real serious shocks. But you do need some diffusion in order to smear the shock over at least 3 or 4 mesh points. So I showed you already the spatial order, the temporal order of the scheme is a third order scheme. What you noticed when we were working on the code is you are always adding to the right-hand side. And it's not this step, it's this step. So what we are actually doing is we are adding to the right-hand side. And then afterwards we are actually multiplying by another factor of alpha. So here's the scheme. It's a scheme which works between first, second, and third order in such a way that you don't need any additional memory. Normally, if you do a Runge-Kutta scheme, you have to have the original time, you have the first, second, and third time, plus an auxiliary array for the right-hand side. You need 5 chunks of memory for a fourth-order scheme in that case. Or you need 4 chunks of memory for a third-order scheme. Here we just need 2 chunks of memory of the full 3-dimensional array. Here's how you do this. You define an auxiliary variable, which is sort of related to the right-hand side of the equation. Your equation is du by dt is equal to f of u. So you calculate u at the previous time, t to the minus 1, multiplied by the time step, and use this as your variable, put it immediately into a W array. So you have 2 arrays only, W and U. And you just add it to the right-hand side of whatever you had. And that's what we have seen. You must never in the code put the df array. This is what, of course, is called df in the code. You must never put this to a certain value. You must always add something to this. And then that's exactly the reason why you have to do this. Because you have to rely on whatever was in the memory before this. And what was in the memory before this was not even the previous value of W, it was a rescaled previous value of W. Now, in the first iteration though, alpha 1 is always 0. Always 0, always 0. And that means that for the very first time step you don't need the W array. And that also means if you want to save your snapshot, you can have a continuous accuracy without having stored any intermediate things. The same is true, of course, of a standard Runge-Kutta scheme, but it's not true, for example, of an Adams-Bashforth scheme. If you do an Adams-Bashforth scheme, you have to use the current and time step and the right-hand side. You have to store 2 arrays, as we have been doing for many, many years. Which is sort of stupid, you might think. So here you don't need that. That's good. That's,
Do you know
this is
sixth
called.
sixth order of this procedure?
You can't. And
It exists? Sixth order of this procedure.
some version of this exists, but they are not exact sixth order schemes.
Fourth, no, it is just four, five,
Yeah,
six.
yeah. I mean, I come to some somewhat funny or curious aspects of this in a moment. Because you have different, these are not unique coefficients. You can come up with different choices of these coefficients, and the scheme stays always of the same order. So it's not a unique choice of these coefficients. And I think the reason is that it's only third order with respect to all linear terms, not with respect to nonlinearities. So if you do a first order scheme, then first of all this one is 0, then this is directly the right hand side, and your new time step is immediately given by the right hand side. Beta 1 is 1. That's just a standard order scheme. The next what? Or Euler. It's first order Euler scheme in time. The next order is one which essentially corresponds to the so-called midpoint formula. You calculate the right hand side, calculate an auxiliary array, which is just the same then in the first step, and the next, and then the right hand, the intermediate variable u is given by a half times this df by dt, and you advance yourself by half a mesh point forward. So essentially, you have the u variable at half the mesh point into the future, half the time step into the future. After that, you calculate the right-hand side based on this previous iteration. So you calculate the right-hand side based on a first-order Euler step halfway into the future. Add this to your previous w array, w variable, and add the whole thing in. And that corresponds to the so-called midpoint formula, where the which essentially means that you have ui is given by ui minus 1 plus delta t times f evaluated at the time ui minus a half. So that's really what it means. And you can do such a calculation, in this case, iteratively by not allocating, by not keeping in memory this together with an immediate time. You have avoided calculating anything twice. Or saving more than needed. So this was as far as the time step is concerned, and one can then ask the question, of course, how does the code perform? People again are thinking, why do you go through all this trouble? Can't you just have a somewhat shorter time step? I mean, the reason why we want longer time steps is because doing a longer and a higher order time step is, the advantage of using a higher order time step is you can use a longer time step. So here's how much longer it can be. For our standard third order time step, we can go even to a 1. 100% of the so-called CFL condition. CFL condition means that the time step is given by, the time step must be less or equal than the mesh divided by the speed of sound, or the speed of any waveform that propagates information through the mesh. The number in front of this is what is called the CFL condition. So I call it here C sub CFL. So in this case, we do the calculation with 70%, and most of the time we do 40%, but this code is actually stable all the way to 1. And we should maybe use more often larger values, because it makes it faster. However, if you decrease the order to second order, you can really not afford doing much more than 20% of this. So this ratio is more than 50%. If you then go down to a first order scheme, the code becomes already unstable for 100
times.
In time.
Because if you do second order in space in time, then you can go to 1. It's only because we have 6 order in space that we have all the cushions.
Is that true?
Yeah.
We should check this.
First order now in space and time.
That will be our third
one.
That will be our third exercise. So then, if the two of you can do that,
we use one.
you use first order and second order in space. Okay, we can do this with the code. You just compile correspondingly. So we do it after the break. Shock tube test is one of the standard problems that are being run. Here is, of course, how our code performs. And what you get is, it's very easy to initialize. You have an initial pressure jump by a factor of 10. Pressure is here 1, pressure is here 10 on the other side. The initialize a wave, the shock front, which propagates to the right. And you have an expansion wave, because you lose all the gas is disappearing to the right-hand side. So the pressure and density decrease, and that's the so-called expansion wave. You have in the middle an additional shock, which you don't see in the velocity, except for this little bump here, by the way. And this is called the what is it called?
Entropy wave.
Entropy wave? There's a jump in entropy, by the way, at the same position. Yeah. But it's called the discontinuous. What is it called? It's an entropy mode.
Maybe name.
It's the
Entropy called entropy wave. Entropy. No, entropy. No, wake or something. Entropy wake.
What's this? Nobody listened to any shock lectures before. What's this thing called here?
Yeah, entropy.
Standard name. No.
It is to entropy.
Do you remember? But you know that there's a name, right?
Yes. But
nobody remembers the name. It's called the contact discontinuity.
Oh.
Have you heard about this?
Yeah, but when it disappears,
so that's called the contact discontinuity.
Something left in on the switch. Yeah, that's called.
So actually, this was not actually the pressure. It looks like a pressure, but it's actually a rho. So you don't see such a structure in the pressure. And so any code, therefore, which evolves the right-hand side, u by dt, with respect to the actual pressure, is okay. There's no jump in the pressure, and you should therefore never produce any little spurious thing in here. However, the way how we solve for this is not through this, but we are solving through this by cs squared multiplied by the gradient in logarithm rho plus the gradient in s. In our units, it looks like this, otherwise some factors. And so obviously you have therefore two jumps which compensate each other. And if they don't do it precisely, you have a little bit of something here.
How many points do you have here?
This was with 400. I think that's the standard conclusion here. What?
No.
And when you look at how many points you have, here's one mesh point. It's pretty sharp. Here's one mesh point. Here's one mesh point, and then the next mesh point is here. So resolving the shock with a constant. Here you have, of course, a diffusivity. This is actually not even a numerical diffusivity. That's what I would call a physical one, because it's a constant one. It's constant in space. So that means you are diffusing everywhere. And that's, of course, why this becomes somewhat smooth. But even other codes they never have a sharp thing here. You can make it somewhat cheaper by making the diffusivity like in Smogrinsky already, but that wouldn't work for a shock. You can adjust it by making this a non-constant thing. It would only pop in those places where you need it. One should not a priori trust such a thing. One should do a double check, and we have done such a double check, and we find that small-scale dynamo action, that's where it does exist, even with an artificial diffusivity. There's a few more pages that I have here about the pencil code. This was a page telling you a little bit about the growth of the code over the last decade, where we have seen that the number of tests with which the code is being tested every night. This was, of course, I didn't really say this yet. The code is developed by, at the moment, 47 people, and if I add your Google account, then it's 48 people. And if Irina checks something in, would Petri's code all of a sudden screw up? And the way to check this is by running an auto test. So first of all, if you really did this, I would ask you, did you actually, first of all, read the manual? In the manual it would say, run the auto test before you check something in, and make sure it works. If it doesn't work, don't check it in. But often it's a compiler thing. It may work because of certain compiler things on your computer, but it doesn't work for Wolfgang's compiler, of course, because he puts all kinds of...
I have a question. What do you mean when you're speaking about after tests? What does it mean? Because...
Okay. Auto test means that if everything is correctly installed, and you go to your computer, on any window. So here, for example, we are in a window which is unrelated. It's actually, in this case, some runs. It's nothing to do with square where it's working.
Okay, low battery.
What?
Low battery.
So all you do is you just say auto test. Okay?
Activated.
Yeah, but this is because of the previous warning, which was suppressed now because it was in PowerPoint. And now on battery. So it runs now in auto test, and this will take, I think, 2 hours to run. There's a short form of this, and it tests everything. But at the brighter day, for example, so I'm going to get out of so if you check again whether anything was working, you will go to the pages. Oh. But wait a moment, I have that possible. I thought I'm. No, it's pretty much in the short. So, yeah, let's stick under Unix here. This is good. This is Unix. Here's Unix. But here I don't see somehow the one of the Windows is really did. Here was this. And what did I want to do? I wanted to auto test. So we checked under the pencil code. So we go to the. I mean, first of all, you just Google it, of course. That's the thing you will find it. You find Google pencil code. Pencil code. Let's see whether you find it. And you find it, of course, right at the top. You go to the Google page. Now again, but this one what we wanted. We wanted to check the results of the test. So here you see the test results, and you see that, and that was run last night. And there's the no modules works okay. The most modules has a problem right now, and this is since a few days, and we have not solved this problem yet. But all the other ones worked. So when we had, for example, the pencil code meeting, everything was working, and sometimes certain things are not working. This could be related. I mean, I don't think this was me who did this, but I think it was perhaps.
So actually, until now you haven't
blocked. What?
You haven't blocked for mean field, right?
Yes. Yes, we always had this, by the way. So already since 2004. So since 2004, we have been solving mean field problems also with the pencil code, including dynamical quenching, of course. 2004 was the year when there was this meeting in Cambridge. So at that time, I did 2-dimensional or dynamically quenched cases. Here we see the number of routines is now on the order of, or the number of modules is actually. The number of modules has increased to something like 260. The number of lines has increased to 150,000. However, back in 2002, in January, the number of lines was on the order of 20,000. So the number has not increased exponentially, it has increased linearly. And even somewhat less than linearly. So it's amazing how systematic this increase is. The pencil code has been used by a number of people who have been seriously working with this as a production code. It has always been a production code. And we have regular meetings. The last one was in Heidelberg, and the next one will be in New York. 2010 and 23rd through 25th, so 26th of July. Yes, a little bit of MHD. We solved in terms of the magnetic vector potential. Why is this good? People think if you then calculate the current density, it's a double curl. Isn't that a bad thing? You have to take two derivatives of something. However, if you consider the full loop of doing a Alvin wave, which can be written in this simple form here as a one-dimensional thing, you see that for an Alvin wave, in order to complete the loop, you have the first derivative in the Lorentz force, in the D formulation, and you have another derivative in the induction equation. However, if you do the A formulation, you have now two derivatives for the Lorentz force, but you have no derivative anymore in here. Which is better? Doing two first-order derivatives, which you know have an infinite error at the Nyquist frequency, Or is it better to do once the second order derivative, which has only a finite error as an Nyquist frequency? Clearly, it's this one. So why does everybody say the B formulation? The answer I got at the last meeting in Los Angeles in 2005 was that we have worked for 30 years with this formulation. For 30 years with this formulation. We have studied this formulation so well, we know everything about this. Why give it up? I was about to say we have worked on this only for 10 years.
You know,
We have worked successfully on it. When I heard the talks about this, they are, of course, spending the rest of the talk about the ways of the divergence cleaning, how to avoid divergences. This is a serious issue, of course, which is simply never an issue here.
Yeah, no, but maybe this, your formulation is not conservative.
Yes, it's not conservative.
It was not the first order is conservative formulation.
So our code is non-conservative. So people then say, how can you ever conserve mass? So the mass is not accurate to machine accuracy. It's only accurate to discretization error. So if you find a certain decrease in the mass, and if it's too big, you know you have to have more mesh points. If you have too few mesh points, you find, what's the problem? The mass is correct, the energy is correct, momentum is correct.
More density to the Gurney relations.
And maybe you even publish a paper then, because you think everything is correct, but you have not actually been able to check this in an independent way.
Actually, but more density with the Gurney relations incorrect in your formulation. That's why I make mistake. Then you can discover.
Axel, but it is checked automatically, conservation of mass in
No.
No?
No.
So you have to check all time? Or
Yes. Yes.
and what to do?
I mean, it is certainly an important issue, and my answer is maybe a bit too rough here, and we should think about it more carefully. And the pencil code has never the philosophy of having only one mode of operation, as you have realized by now. Just about anything is possible. If you want to do a non-conservative or a conservative code, you can do this. You just make a mass underscore conservative. And Petri or Piali or somebody may make a mass underscore inelastic. You can just do anything you want. That's it. That's the philosophy of your code. If you want something else, you can do it. If you want to have a code that is adaptive, you can do it. We have started discussing it, but nobody had the time to do it because the code is used for production runs. It's produced to do write papers. And if it's all of a sudden becomes absolutely critical, and then you will be fast in doing whatever is necessary to do.
Most people use conservative formulation because they want to compute software security.
Yeah, right. And they don't. Yeah, they don't care about. Yes, exactly. They don't care about whether it's correct in 1D or 3D. And they don't care about turbulence. And they wait until somebody else tells them, yeah, it was actually correct. But they were not able themselves to find it, to tell that it was correct, or not able to convince others. They may have believed it themselves. Paul Woodward actually told me that he knew it was correct back in 1998. He knew it.
Who?
Paul Woodward did the calculation with the bottleneck effect.
Oh, bottleneck.
Yes, and he says, I knew it all along. But if you ask anybody else whether they believed it, the answer was no. So here's finally the demonstration of the comparison. The point, of course, is this is what I said is only valid for schemes which are centered. If you have a non-centered scheme, you can make the two equivalent.
Axel, is it true that bottleneck effect was found by Falkovich or not?
It's an important paper, certainly, which we quote all the time. So here you see a little articles in the B formulation, of course, the A formulation. Falkovich, 94, but there was a paper by Shea and Jackson in 93 where they had the fit to this. But I think the term bottleneck was probably coined by Grigori.
Falkovich,
What did he say?
Grigori.
Yes. So here you see then for the B formulation at lower resolution 64 cube you see much bigger figures. The reason, of course, is completely obvious now. Yes, more about the power spectrum here, k to the minus 3 halves, by the way, is the power law here. Back then we also didn't know whether that's really what we are supposed to get, but now everybody else gets also k to the 5/3. This was already back then in 2003, 1024 cube.
The slope 1 point what?
1.5.
1.5.
This is spectrum of what?
A lot in the code is being done by doing the analysis, the data analysis online, calculating power spectrum during the run, calculating all types of visualizations during the run. Because if you put your 1000 cube snapshot on your laptop afterwards, you will have a problem not only with your disk. If you think you couldn't do a shocks, of course you can do a shocks. Here's the Mach number 10 run of force turbulence. Mach number 10. Shock force turbulence, yes.
The question is how accurately do shocks. No?
How what?
The question is how accurately do
Yeah.
shocks. That's not that you can do this with.
Yes, there I would agree. There are issues. As I said, theoretically speaking, if you don't believe something, then you should make the resolution twice as high, and the solution should become 2 to the 6 power better, which means 64 times better. This was simply shear flow turbulence, and incidentally, you see this convergent flow inwards. Is there a problem with mass conservation? Who says yes? Who says no? Mass conservation violated? No?
You should check it.
What? How to check?
You should check it. Operate it.
So the reason is you have structures in shear flow turbulence that are inclined. Of course, they are systematically inclined. If you have an inclined structure moving through the mesh downwards, the point of, or if it moves upwards in this case, the point of intersection moves to the right. And if you're on the other side of the floor, it moves to the left. That's the reason why it looks like it.
So here there is generation of vorticity due to the shear. Generation of structures.
It says vorticity, of course, but there's not much structure in the vorticity. And now one thing, however, that I overlooked back then, and then Papaloiso and Heinemann found this afterwards. And I had the simulation already back then. I saw this stuff here, and I thought I better don't show it to anybody because it looks like there's something not very resolved with the density. It looks like crazy.
But it
Right?
is
So,
just hydrodynamic calculation
yes.
without one.
There is MRI, by the way. It's
MRI.
MRI, yes, yes. This is really, and I think this has to do with the video.
With magnetic field.
So, this calculation has been such an important thing. You see these slides as well. It has to do, I think, with the MPEG thing, the MPEG encoder. This was such an important, the understanding of this, which is understood now as a density wave, has been such an important thing that Toby Heinemann got an offer, first of all a postdoc offer already 1 year before he's finished his PhD, 2 years after he started. And not only that, he got another offer then from Princeton. And so now he's in Princeton already. So this has been an important discovery for him. Here's now Petri simulations. One of the important calculation or outcomes of this is, you'll see the sun is full of, or the convection box is full of thin flux tubes, right? And we see flux tubes at the surface. However, what happens as this dynamo actually runs into saturation? Where are all these thin flux tubes? The magnetic field has become much more diffusive. So the idea of thin flux tubes is something that was justified because thin flux tube is something that we see at the surface in the form of sunspots. It is justified by kinematic calculations, but it's not justified by successful large-scale dynamo actions. People have been trying to find large-scale dynamo action. If you ask whether the dynamo is successful, and what you should ask is, how does the dynamo look like when you increase Rn? And I have been asking Fritz Busse, and we should ask him again on Friday. On at least some of the simulations, he tells me that if he increases Rm by a factor of 2, his large-scale field, the overall magnetic field increases, but his large-scale field, which you obtain after averaging over the toroidal direction, decreases. It decreases only by a little bit, by 40%, which means it's compatible with a decrease of B large scale, or let's do the RMS value of the large scale field indicated by an overbar, which means the toroidal average. You normalize this by the total magnetic field, RMS value, and this should decrease like Rm to the minus 1/2 if you are not a successful large-scale dynamo. Or if you have one which is catastrophically quenched, I should say. That means if it has open boundary conditions and it.
What part of the Sun you model here? What part of the Sun do you model here?
I mean, it's a parallel box. The magnetic field extends over the entire scale of the box. The Sun is not a box.
No.
So we cannot really seriously say that we are simulating a part of the box. However, it is a box which has an overshoot layer here.
So this is here small scale dynamo or not?
Yes.
What?
Here there is small scale dynamo or not?
Yes. Bottom of the
Which
connection.
there is, of course.
there
The
is.
Reynolds number is 120, and if you think 120 is small, you multiply it by 2 pi, and then you get a number which you may find bigger.
So here there is generation of
Yeah. The critical value is around 30 for small scale animation. And this one is
for large scale dynamo. And for large scale dynamo, threshold in Reynolds practically 1.
Yes, exactly. Exactly, absolutely. So the threshold is 1. So here you see, as the dynamo runs into saturation, the scale, the scale of the beam becomes more and more large scale. I've taken only part of Petrie's animation, namely the part which is rounded around this corner where it runs into saturation. So that will stop fairly soon. One of the little items I put down here is, people sometimes say, if I make the Prandtl number smaller, so large-scale dynamo action, as we know, does not depend on the, it only requires that magnetic Reynolds number is larger than 1. It's independent of the Prandtl number, otherwise. Small-scale dynamo action, on the other hand, is very different. It depends very sensitively on the magnetic Prandtl number. When I was telling Sascha Brun about this, he was telling me if he lowers the magnetic Prandtl number, he loses the dynamo. And the reason for this is simply that there are 2 different conditions to be obeyed for the 2 different types of dynamos. For a small-scale dynamo, the Reynolds number has to be larger than the critical value, which is 30 when the Prandtl number is 1, but is already on the order of 300 or 400 if the Prandtl number is 10.
In a principal case, even 600.
So this is very difficult to obtain. However, for large-scale dynamo action, the condition has nothing to do with the Reynolds number, except that it is bigger than 1. That's very easy to obtain. However, there's another very important condition, namely then the condition that the dynamo number is larger than unity. And the dynamo number is a product of 2 numbers. For an alpha omega dynamo, one is having to do with the alpha. As far as mean field calculation is concerned, we have always been used to the fact that the alpha effect is something like a free parameter that we can just choose. So if we want to have the dynamo mean more active, we just make the alpha bigger, or we make the rotation bigger. However, if we express this actually, as we are now understanding this in terms of physical quantities, C alpha is essentially the degree to which the turbulence is helical, epsilon f at the small scales, multiplied by the scale separation ratio, kf over k1. So if you have your given turbulence, there's no way that you can make C alpha bigger. If you force at wave number 5, and your box has wave number 1, this ratio is 5.
If you've got maximum case.
Yes, this ratio is still 5. If this is 1, then this is also 5. And if, of course, you make this one smaller, then it becomes less than 5. Less than 1, eventually. So an alpha squared dynamo would already not work if you make the degree of helicity too small, and have not at the same time sufficient scale separation. You can always compensate the two. So, for example, in convection, and we should actually check this for convection. Have you checked this? Epsilon f. Epsilon f, if you don't know what it is, it's given by, epsilon f is supposed to be calculated as omega dot u over the relevant chunk of the domain, divided by u squared, and whatever you choose to be your kf, which would hopefully be the wave number where the power spectrum peaks.
This is non-rotating convection, yeah?
No, that would be tried, of course. No,
Yeah.
this would be true now for Petrie's simulation, for any simulation. And the idea is to work this out. Can you do this in the next 5 minutes?
I have it on the table, actually.
Actually, that's, yes, because of course, I have been making this comment, of course, before.
Right, so it's something like 0.05 for this regime.
0.05.
Right.
So Petrie has, for real convection, it's not a free parameter. it comes out to be 0.05. And so, yes, and is that true even for the alpha square Dynamo simulation? Is rapid rotation?
For that, it's somewhat larger.
Yes.
I don't have data for that, but it's.
And then, of course, the kf over k1 has to be in the inverse of this, at least, and now that for this product to be 1.
Actually, here maybe also C alpha can depend on stratification.
It's not
Because
solid.
if you have shear
Yeah.
and
No, but
so-
this has to do with the fact that the vorticity, helicity, I mean, this is an approximate formula.
yeah.
And the helicity production, of course, has to do with stratification and rotation.
Yeah.
But you can impose steering force with helical steering force. It doesn't depend at all of any clarification or whatever.
Yeah, of course.
Of course, you can do whatever you like.
Yeah.
Until
Yeah.
Yes. In that case,
Was the real convection or was forced turbulence again here?
this was, of course, convection heated from below. This is
No,
lower
it
voltage
doesn't
layer.
depend of nature of
Natural convection.
Convection maintain this transition layer.
That is being maintained by an opacity profile or rather conductivity profile, which is prescribed, as it was done in many such simulations. You may think doing a Kramer's opacity is better, but it is actually worse in the following sense. You are never able to do realistic convection because there's a huge gap in timescales in real astrophysics. The thermal timescale is so much longer than the acoustic timescale. You cannot capture both of them in the same calculation.
But then it has nothing to do with reality.
That's correct. It has nothing to do with reality. That's the case for many such simulations. The way how Oke has been avoiding this is by simply setting up a simulation which is very, very close to the final state by just having a very smart setup and rescaling the fluctuations as you go to bigger domains. So this is something for which you can't do a simulation from scratch. You have to do it by just having the final state essentially and just looking for the modifications. Yes, exactly. So that's therefore Analytic of course helps. Radiation transport is a non-local problem. Can it possibly be parallelized if it's intrinsically non-local? The answer, the equation is what?
Huh? Cartesian.
Cartesian. Yeah, Cartesian. You want to solve the radiation transport equation. What you could think of doing is you integrate, you have a ray direction, you have a certain amount of light coming in here, you integrate along the ray. What should this processor do when you don't know the radiation of this that comes into this processor? It has to wait. So you do the calculation, ding, 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 everything, and then the last processor finally says, oh, now I can run some calculation. That's as quick as a single processor calculation. We have not made use of multiprocessors. You want to really keep all processors busy at the same time. With this, you can't do that. The way to do this is to to actually solve this analytically partially by splitting up or by writing down the analytic solution for this. The analytic solution is given by an integral plus an additional factor which has in it the incoming radiation plus a factor which involves the incoming optical depth tau. This is something you don't know. You don't know what is the incoming radiation here, as I said. You don't know the optical depth at this point either. Because that one you also have to integrate. It's not very hard, but you still have to integrate that. However, here you have an integral which just depends on the difference of the optical depth along the ray. This calculation you can do straight away. You can do this calculation on all the processors immediately. So let's start the calculation. Everybody does this integral. Nobody knows the real answer to this yet. And after they've done this, they communicate finally the final tau at the end of the processor. They communicate this to the processor that is connecting to the same ray. They are telling you what is the intensity of the outcoming ray, outcome of this integral. What comes out here is being added through all the processes, and then you know that. So this is a simple calculation. It does not involve any accessing of intermediate points. It just is some management keeping where you have to know the beginning and the end. And that is a global calculation. For this processor to know how much comes in, it has to wait until the information is propagated through everything. But this is a fast process. You don't have to wait for any serious calculation.
What's that? That's the kind of propagator.
Yes.
on the integral?
So it is sometimes
No,
depends.
sorry,
The type of propagator.
It depends on the problem.
I'm not sure how the answer should look like. I mean, here you see the differential equation. It's a simple differential equation. However, it is harder because, of course, I is not a function of just a position and time. It is a function also of direction. So therefore, and then it's x and c. So that means you have, but in practice, we solve for this by choosing, in our case, 26 such rays. That means these are the rays that you have which connect with the nearest corners in your three-dimensional box. 26 is 3 cubed minus 1. So the first calculation consists in doing the integral on each point. Then you have to do the communication part. That is, you have to communicate this guy to each processor, and this has to be in a sequential way. And then finally you have to add the two together, which means you calculate the amount of heating on all the processors.
It's so simple. Boundary condition is simple.
So this is the calculation of radiation transfer. It can be done in parallel. Here's the advertisement about the Zinder school. If you have any students, as I said already last time, please send them to the school. Here's something more about the Euler potentials, because I skipped that. Here's how you write the magnetic fields. This is actually well known to people in the plasma community. Irina knows this. Maybe it's mostly it's known in the plasma community. The nice thing about it is that the actual solution to the induction equation, dP by dt is equal to curl u cross b, this complicated curl cross b, is just being solved by simply advecting alpha and beta. The same solution. Very simple. Of course, if you then do an SPH calculation, that means each particle, you choose a value of alpha on each particle, you choose a value of beta on each particle, each particle keeps its value of alpha, and you have done with your simulation. You just let the particles go. Amazing, right? You just let all the particles advect through the mesh, and they just keep their thing. And afterwards, you assemble your B again, you have your B. Amazing. And this works only if there's no diffusion. Now, not doing diffusion is not very good.
Yeah, okay. It's funny because alpha and beta diffuse, although they
They
does
diffuse
not
only if
necessarily.
you go to this line. Is that what you mean?
Yeah, but especially because B doesn't diffusion necessarily.
Yes.
But B does not decay, otherwise you would have
So, now, if you want to add diffusion, then you can say that's not correct. Then it is not correct anymore.
No solution, you mean?
Then it's not a correct solution anymore. And then you have to say, what the heck? Let's just make it very, very small. Nobody will notice this. Make it even as big as the discretization of your scheme is. I don't think I have all the material on this here, but here, by the way, is the analytic calculation of, that's in the appendix of my paper, which is now already through the proofs stage. But here's the calculation as far as Roberts-Square dynamos is concerned. So one thing was clear from the very beginning: you cannot do helicity with this thing. You cannot do helicity with this thing because, as you actually see from this, it's quite amazing. Look at this. So you can, of course, write down the vector potential, either as this or as its vector potential. You could, for example, even just write as alpha times squared b. Maybe that. It's like a monoclinic term or something. If you take the term of this, you obtain, of course, this one here. But look at the dot product. This one is in the direction parallel to the gradient of beta. This one is perpendicular. Dot product is always 0. In the paper by Stern in 1970, he says it's just a gauge. The helicity being 0 is just a gauge. And it's true because you can always find another gauge transformation to make locally A dot B different from 0. However, if you talk about a periodic box or a box with perfectly connecting boundaries, the helicity A dot B is gauge invariant. So even if you can make it locally different from 0, Here it was locally if always equal to 0. We can make it locally different from 0. If you integrate it all up over volume, it must be the same no matter what it was in between. And so, if it was always point by 0, in one calculation it must be 0 in total. Yeah.
So I still don't understand it. For example, if you have alpha and beta exponentially decaying, beta is going to decay, so there's no Dynamo. I mean, just for this particular solution. If alpha and beta exponentially decay, I mean, when you put the gradient of alpha and beta, they are already exponentially decaying. The product is exponentially decaying, and there is no B at all.
Yeah, exactly. So
there's no
part of the
Dynamo.
inside of how it can happen. You can still have, of course, amplification.
Yeah.
And this is because you can develop arbitrarily large gradients by bringing them very close together.
But this is also natural because it is not a solution if eta and mu are not equal 0. If eta not equal 0, you cannot build this solution. But with eta equals 0, no Dynamo.
Yes.
So in some sense, no contradiction.
There's no contradiction. No.
It's very easy in some sense.
So first of all, you may think the problem is related to the fact that here, in this particular experiment where we look at the Roberts flow, it doesn't work because I was just doing a particular kind of flow, Dynamo, the Roberts flow. This is very special. Roberts flow is a slow dynamo. We are interested in fast dynamos. We may even be interested in dynamos that have pointwise 0 helicity. If you do such a calculation, you still find decay.
But you should first to solve, and just after that, tens.
Yeah, exactly.
It's a problem.
This you can't do. This you can't do, and that's why actually one is fails. However, even for cases where there is no dynamo, where you just impose a magnetic field, do you think this goes wrong? The answer is that.
Maybe not if you don't know it.
But the answer does go wrong.
Yes, it's interesting.
So you impose a magnetic field, you do it in 3D, you get more power at small length scales. It becomes even worse if you do the nonlinear problem. What? Yeah.
But just in small scale it's wrong. In large scale also wrong.
Exactly. So therefore people, the advocates of this technique have said you can at least get some kind of an idea. You see a trend. So in some sense you see a trend. But of course, whether it's going of decaying, you still don't know. But you know that something is going to change. And that you know whether it was methods, of course.
Is it just because reconnection cannot kill the small scale? Is it all?
Reconnection is a necessary ingredient in any dynamo.
No, I mean just the difference between the two lines. Was it just
the difference can be boiled down to the following insight. Just take a very simple, so that was one thing. Helicity, was helicity the reason? The answer is no. Because it does fail also for complete non-helical things. Is it that we only cannot do dynamos? Can we do everything else? The answer is no, because you have seen too much excess power at small length scales. Is it because you're doing 3D as opposed to 2D? Does this method fail just because we are doing 3D and everybody else has been doing 1D or 2D?
The method, if you...
Or the Versation method.
It's 2D. It's 3D.
Now I'm having here a problem which is 2D. Does it work or not? Very simple, right? It's even just one component of the magnetic field. Rainer, what do you think? This method can possibly not fail, right? With such a simple thing. It's just one component of the magnetic field.
No, but I mean, if there is no reconnection, then this
No. Now I'm doing actually just a decay experiment, so it's full. I want to isolate what exactly is the problem. The problem has to do with eta. I was explaining that there is no such physics with eta equals to 0. Such physics is not meaningful.
It's another physics. It's another.
It's something which you can put on paper.
Yeah.
But if you want to publish it in Nature, you have to make sure it really happens in Nature, and I have not found such a thing.
No, in nature it can publish.
If I remember correctly, I think these potentials are used mostly for magnetostatic
Yes.
plasma field, so that
Yeah.
that might be the reason why they don't.
People have probably understood it. But of course, in order for
I
everybody else to understand it.
something that is not.
I think I've seen it being implemented in SPH computations now,
Yes.
where there are these particles, and it can be easily implemented probably,
Yes.
but it will be equally wrong then.
Of course. So therefore, over the last 2 years, I have been hearing people talking about this. I've been telling them, can't you just solve a simple problem where we know it works, like a Roberts flow or something? And it's very simple, but they never actually did it for me. And then there was a plasma physics meeting in Sofia. And then on this one evening I thought, this is getting too boring here, let me just solve. I mean, these are two advection equations, right? I mean, with the pencil code what I did was I just pretended these are two passive scalars. And I just coupled them. So in a matter of like 15 minutes I had the answer. And then I knew it doesn't work. And then I thought, wow, if it doesn't work, everybody else thought it won't work, then it's maybe worth the paper. So I finished the paper by Sunday then after I came back. I wrote it up, typed it in, and then I went on holidays, and then it was already submitted. So that was, it was just because, but look at this thing here. Look at this thing here. So what can possibly go wrong with this? The reason is, so you have actually two different choices of how you can write this. And in one way it may actually still work, and the other way it doesn't. So if you calculate it like this, you write alpha as this, and beta as this. Then you, of course, you find that the gradient points in the y direction is proportional to sine x, sine y. That's one of the components here. If you differentiate this one in the x direction, you also find sine x, sine y. It gives you a component in the x direction. The cross product gives you one component in the z direction. Yes, and you reproduce your solution with this. However, both are harmonic functions with a wave number k equals 1. Both will decay at the same rate, and you get a decaying solution. However, this solution, this is no longer an harmonic linear harmonic solution. It will not decay as a wave number like the wave number 1 thing will decay. So already this representation is wrong. The reason why it's wrong is because both alpha and beta depend in both cases on the same coordinate, which is y. This depends on y, this depends on y. In that case, this term, which is a residual term that stays over, if you do the analytic calculation, we find that this term must vanish in order for this calculation to be correct. This finite eta. This one would be finite if both alpha and beta depend on the same coordinate direction. One way to escape this is to move this additional sine y dependence also to the other side. So alpha becomes then the integrated form of cosine y, which is this form here, and beta is just the rest of this. In that case, the calculation works, but then this one will decay at a higher frequency, at a higher speed, and this one will giving you the correct answer, which is slower. So with finite eta, it normally doesn't work, only if you manufacture this. So that shows you that already in 2 dimensions, the method is wrong. So many of the answers that were given, a bit like the beginning of the lecture where we came up with 5 different reasons why something could go wrong. Here again, there were 3 different reasons why it could go wrong. And we didn't actually know until
no reasons to it is correct.
Have you tried to do the same computations in the no-Euclidean background?
Euclidean?
No Euclidean. Not Euclidean background.
No.
Yeah.
Okay, so as far as the tutorial is concerned, the thing we have to do is go to the web page, go to the pencil code page. It's still working. I am connected, supposed to be connected still. Am I not connected? Here we go. So one other way of finding it is to find software on Nodida. And then go to the pencil code, find the same page, and you find the numerical experiments page. There's a number of different sessions here. Let's go for this one. There's first of all something that you have to learn how to set up the code. There's a lot of Python and stuff like this. Here, the effective wave number is the first exercise. Patty knows it, of course, but does Patty also know how to calculate, how you tell everybody else to do it? The way to do this, so people may not know that how to do such a calculation. You have to divide by sine kx. That may go infinite, right? So how can you possibly tell somebody to calculate effective wave number? Somebody who does the Zeus code. There's actually a way out of this, without dividing by anything. All you have to do is just take the derivative of not only cosine, but also of sine. So take a derivative of the curl of a quantity like this. People will recognize this as the Bernoulli field. Taking a curl of a Bernoulli field will give you the same field. you dot it with A again, you obtain B squared. And so therefore you can calculate the effective wave number as just A dot B divided by B squared, which may be 1 if you have a good normalization, or A squared in this case. So that's what you do. You just put as initial condition, as it is of course available in the code, a Bernoulli field. So here's how you do your tutorial. You click here, you find all your input routines. The code is given by 2 local things. One has to do with the resolution. So here you do the calculation with one processor, no reason to do multiprocessor. You do 128 mesh points in the x direction, and 1 in the y, and 1 in the z direction. You then do a makefile. You use no hydro, no density, you just do magnetic field. And the reason is that in magnetic field you have your Bernoulli field implemented. Then you look in your start.in file, and you find your initial condition is given by a Bernoulli wave number, with the Bernoulli field varying in the x direction with a certain amplitude, and a certain wave number, which is here 33. Which is very close to the Nyquist frequency, which would be 64. Finally, you do the run, and you do it for a maximum runtime of 0. T max is 0. The reason is you don't want to actually run, you just want to get the diagnostics out of this. And the diagnostics is A dot B. No reason for every time advance. So that's how you do the tutorial. And you find answers. The answers are hopefully all available. Here's the answers. So you do calculations for different frequencies. This one was at 60, Nyquist frequency is 64. And for each value you get your A or B. And you put this in a table and plot it. That's how you do it. You can do the calculation with your favorite derivative scheme. You can replace it with a 6-order scheme by a low-order scheme, which sometimes I have in this. I have it in the same page, I believe. No, I don't somehow. This was because it's really up to date. Yes. Anyway, some other pages have higher orders and results as well. Ablaction test. You ablect your smooth thing then. You see several ones? Yeah, here's several ones. Here you can do it with higher order. Different Coulomb conditions. Nonlinear sound waves. So if you don't want to look into those files, which tell you all the details, you can actually download the entire tar file, which is here, and compile the code with that. There's a number of different examples, including also helical dynamos. You can run helical dynamos with as little as just 16 mesh points cubed. Imagine the cowling problem was such a big problem for such a long time. People didn't know whether. Actually, if you look in the paper by Lamor, 1 year after Cowling's paper, the impression was that Cowling really meant that dynamos don't work in general. That Cowling's theorem only applied to 2 dimensions was, of course, clear, axisymmetric, but it was not regarded as a crucial point. I mean, it was not regarded. I mean, if you look in the discussion in 33, 33, which was only after Cowling was maybe 35. Maybe. Yeah, we'll check. If you look in this, I don't think there was any mentioning of this being crucial. So rather, it was thought that maybe there's a completely different reason for having magnetism on the sun. Not simply the idea of Lamor that it was a hydromagnetic dynamo was simply disqualified, and was said that Lamor was simply wrong with his idea. And then Lamor said if this idea was wrong, then there would be no theory for dynamo for magnetic fields in the sun, even remotely inside. Now we can do all these cumulative simulations at rather low resolution. Here's yes. 16 mesh points cubed, very poor resolution. So you see mostly random, but then you see that a large scale magnetic field you obtain. If you run the simulation, you get this is repeating, of course. You find this result after just a few minutes with this code now.
Axel, when you say Cowling theorem in 2 dimensions, are you referring to flat 2 dimensional? Okay.
As you know, right?
Yes, just-
In negative curvature,
to be clear.
all hell breaks loose, perhaps.
Mm.
Connection between physics. Yes. Meters, okay. Burger's shop. You can do Burger's shop. And place oscillations. And you have a number of different mixed topics. MRI in 1D and 2D. Albion waves with dimensions. If you want to do dimensions, how will you do this? What are your dimensions? You can choose in the philosophy of the course all kinds of units. You can use non-dimensional. Often it means for us CP is 1. That's crazy if you want to do ionization. CP equals 1 doesn't mean much. It's completely crazy. So this was a good choice in one particular case, but in other cases it's a completely stupid choice. The same is true of all kinds of other things, like mu not be fully equal to 1 often. Often that's crazy. You can make a choice. You can say the system of unit is CGS, but then other people will say, I don't use CGS. I use SI. So you can actually do both. And you can also use units where H bar is 1 and G is 1 and C is 1. So all these things are possible. The philosophy of the code is to be as flexible as possible. So what you do then is you say the magnetic unit is 1, which means you're running 1 Tesla. That basically tells you how big, even if you run as your length unit 1 megameter, you choose as a length unit 1 megameter, as a velocity unit 1 kilometer per second, then clearly mu naught is not 1. It's also not, it's also not 4 pi times 10 to the minus 7. It's this times some other factor which has to do with the c's 10 to the 6 in terms of subfactors, of course. And that's all being calculated in the code, so you can do that. Right, so this was the introduction to the tensor code. And of course the code, as you have seen, works also in multiple dimensions. Here is just a simple solution of the Parker Van. Parker Van is the solution where you go from subsonic to supersonic without going through a shock. Very unusual. Normally you do the transonic thing with going through a shock. With a Parker Van you don't. And then during the tutorial somebody was asking, can you do the opposite of a Bondi accretion? And I said, I don't know, maybe. And so I changed the sign of the velocity field and everything works the other way around and I got Bondi accretion. So, given that you asked one question, which was a question today, you asked me, can you do this and this? And I said, yes. You said doing Euler's step in second order. Then we should do it. But let's get a coffee first, and then I can...
No, actually, maybe most important note is for people some nice special course which deals with mean field theory.